Hi everyone, welcome to today's webinar, Achieving Separation of Compute and Storage in a Cloud World. We are very glad everyone could join us today. My name is Amelia and I will be your moderator. Before I introduce you to our speakers, I have just a few housekeeping items. All participants are automatically on mute throughout the presentation. If you have any concerns or wish to communicate with me, you may do so by selecting questions from the GoToWebinar control panel located on the right-hand side of your screen. Just type your message or question and I will be able to see it. I will be monitoring this throughout the presentation. We will have a Q&A session at the end of our presentation so we can answer all of your questions. To ask a question, select Questions from the GoToWebinar control panel located on the right-hand side of your screen. You may ask your question at any time during the presentation, and you don't need to wait until the end. Lastly, today's webinar is being recorded and will be available for on-demand playback. We will email you the link to the presentation in the next day or two. To get us started, we're going to run a poll first. Is your compute environment independent of your data storage environment for your data-driven applications? Please select and submit. We're going to give 5 more seconds. Great, thank you. I believe that is all the housekeeping items, so let's meet our speaker. We are very pleased to welcome Dipti Borkar, who is the VP of Product at Alluxio. She has over 15 years experience in data and database technologies across relational and non-relational data. She also has extensive open source experience. Prior to Alluxio, she led product at Kinetica and Couchbase, and has also assumed several leadership positions at Couchbase. Dipti, thanks for joining us today. And with that, I'll pass it off to you.
Great. Thanks, Amelia. Thanks, everyone, for joining today. We're excited to have you on today's webinar. Here's a quick agenda of what I will be covering in today's session. So first, we'll take a look at why you need to be thinking about storage-independent compute. We'll then move on to a quick overview of the Alluxio technology. We'll take a look at the reference architecture as well as some of the data flow paths within Alluxio. And then to close out, we'll look at a couple of real-world use cases where Alluxio is being used in production within different environments. So let's get started. So taking a step back, if we look at how the data ecosystem has evolved, we started off with mainframes in the 70s and 80s with the first with the CODS paper being published and the relational model being published. And in this situation with the mainframes, the application, the data processing, as well as the storage and hardware was all tightly coupled. It was all essentially in one box, fully vertically integrated, and there was not much flexibility across any of these layers. As time evolved, we saw the client-server architecture come up, and now applications start to be separated out from the data processing and storage layers. Hardware started to be decoupled, where you had actual physical hardware where you would install software on like a database, a relational database, but the compute, that is the data processing, the query processing, and the storage was still very, very tightly coupled. From that point on, as compute kind of evolved and became much more powerful, we started to look at distributed architectures. And the massively parallel processing type of architecture became popular, where data warehouses or column stores started to be built out, where you got a lot more processing power, but the data and the compute were still very tightly coupled. So essentially, you had to scale out at the same factor. The compute grew as the storage grew, and there was really not much flexibility with that. And then over the last 10 to 15 years, the big data ecosystem started to grow. And as data exploded, there was a need for cheaper storage, more flexibility. And that's where we started to see a little bit more loose coupling of the data processing as well as the storage. So with MapReduce getting introduced after the Google paper, MapReduce was run on HDFS within the same node, and so you still had co-location, but the frameworks were different. MapReduce was a little bit loosely coupled from the underlying storage that was HDFS. And that's kind of where we are today, where in the big data ecosystem, a lot of your compute, whether it's MapReduce or it's the newer frameworks, data frameworks, they are all co-located with the HDFS. And so you have data locality where the data that you're processing on is essentially in that same server, and you can and the speed of processing is faster because of that data locality. You can create very large clusters of Hadoop in a distributed environment, but if you need to grow your compute requirements, if your compute requirements increase, you still have to add additional nodes that are tightly coupled. So you would need to add significant IO capacity as well as CPU capacity. There isn't a model where you can change your compute capacity at a different scale than your storage capacity. And in addition to this, there are many mega trends. There's two big mega trends that are driving towards a new architecture. So when we see our customers and users looking towards a separated architecture, these are the two big initiatives that they're thinking about. With cloud being more predominant, we're seeing the public cloud models more developed and managed, private clouds, hybrid clouds, multi-clouds. And so there's many different deployment approaches with cloud adoption. And with data becoming more and more important, big data processing has evolved significantly as well. So let's take a look at how the data processing has evolved. So if you look back to the big data ecosystem, as we said, it started off with Hadoop MapReduce on HDFS, and it was a very simple architecture. So you had one data framework that was running on one storage framework. It was co-located, tightly coupled. But over the last few years, that has dramatically changed. So not only are users dealing with a lot more different compute frameworks, like Spark becoming more predominant, Presto, along with MapReduce, Hive, as well as a lot of the machine learning, deep learning workloads, whether it's TensorFlow or Caffe, there's a lot more different ways of accessing data and getting insights from data. On the storage front, while HDFS has continued to be important and is widely adopted, there are newer technologies that are coming up. For example, the object stores as well as the cloud stores, whether it's in the public cloud or private cloud, they have started to emerge, which provide it's a cheaper, more cost-effective alternative to HDFS for depending on the importance of data. And in addition, users and customers and enterprises are looking to access even data that might be stored on the network attached storage, like NAS systems via NFS, and have them more accessible to all these different protocols that have now emerged. So if you look at this new ecosystem that we live in, where you have a lot of different compute frameworks and a lot of different storage frameworks, you get to see that it becomes quite complex for every compute framework to talk to every storage framework underneath. And so, now we kind of get to why why do we actually need to independently scale compute and storage, particularly for data-powered or data-driven workloads? Fundamentally, compute is CPU bound, and so it's a different dimension of growth and scaling that it needs, versus storage is more IO bound, where it needs more IO capacity, it has more storage requirements. And so if you have growing compute needs where your applications are demanding more Spark jobs or more Presto workloads for more reporting or data processing, then you don't need to add additional costs from an IO perspective. You should have the ability to just scale out your compute and have it separate and meet the demands of whatever your business needs. And if your data is growing significantly, then you need more storage and you become more IO bound, and you need to have the ability to scale out your data based on your data needs. So these are completely different dimensions, and if they're tightly coupled, you lose the flexibility, you lose all the advantages that the cloud deployments and the cloud environments are now providing. And there's four specific reasons why it helps to have compute and storage independent. So the first one is reduce data duplication. So as more data gets generated, and as more of these compute frameworks emerge, typically you end up copying data into different locations, whether to either to create data marts or to create different copies for those different compute frameworks. And you end up with an environment where you might have multiple copies of the same data, in some cases 3, 6, 9 times. And this adds up cost from an IO perspective. The second one is if you do have a cloud environment, particularly for your compute, you can start leveraging modern environments and orchestrators like Kubernetes to automate that environment and create environments that the business needs. So for example, if you have a workload that only needs to be run certain times of the month, let's say during Black Friday or for a specific gaming event, then you can bring up that compute only for those times, have it separated out, and have it orchestrated by Kubernetes or any other orchestration technology. This allows you to have flexibility for bursty workloads or for peak load times, where you can scale up your compute or scale down your compute depending on the requirements. The third one is you can now leverage in a separated environment different storage technologies. So as new storage technologies emerge, like the object stores, you could use these cheaper and simpler technologies for some of your data workloads, depending on your performance requirements. And so it gives you a little bit more flexibility to reduce your storage costs by using different tiers or different types of storage underneath the covers. And then finally, separation allows you to keep your data, which might be considered your core asset or your core IP on premise, but still leverage the power of the cloud and have your compute located in a public cloud where you can scale as your needs demand. So these are kind of some of the reasons that we hear as we talk to users and customers. Why are they looking to independently scale storage and compute, particularly for the big data ecosystem or the big data workloads and AI workloads? But then as you scale out independently, is it a seamless process? Can the same environment now that we looked at, where you have all these compute frameworks and storage frameworks, do those continue to operate as needed, or are there certain problems and issues that come up with this separation of storage and compute? So let's take a look at what those challenges are once you start separating out these layers. The first one, which is kind of the biggest factor, is data locality. In an environment where you had a MapReduce or Spark job running on HDFS in a co-located environment, that job is essentially working on the set of data that HDFS node is managing. However, when we separate out these environments, you no longer have that data locality. And so you need to create or move that data, have some sort of an orchestration or engineering pipeline to move that data local to the compute technology, whether it's a Spark or a Presto or any other, to make it efficient and to continue to get the benefits of high performance workloads in this separated environment. And so data locality becomes the biggest issue in this separated environment. The second one that we hear about is data abstraction. So data can be stored in multiple different storage systems. And so now when you separate out storage and compute, you essentially are creating an environment where all compute frameworks need to talk to all these storage systems underneath. And that can be quite complex because there's a lot of permutations and combinations. And so it starts to create a need for an abstraction or a unification layer across these multiple storage systems. It could be different HDFS clusters, it could be different versions of HDFS clusters, or it could be object store, a combination of object stores, network attack systems, as well as HDFS. And then the third one is data accessibility. So when you split out and move out compute into a different in a different location or a different environment from your data storage, in some ways you still need to use the APIs that storage system provides. And so if you have a data framework or a new AI framework that you would like to use on your existing data, even if you have a separated environment, it doesn't allow you to do that because either you have to change the compute framework to add support for the storage system API, or you have to change the storage system API to expand the amount of capabilities it provides for this new compute framework. And so these are the three kind of fundamental challenges that start to emerge when you move out and separate your compute from your data storage. So to enable truly independent scaling, we're starting to see the need for a new layer between compute and between storage. So here is a layer where you need to address data locality, you need to address data abstraction, as well as make that data more accessible so that all these compute frameworks on the top can leverage the plethora of storage systems underneath the covers. And that's where Alluxio comes in. But before we move forward, it's quite interesting for us always to learn about what compute frameworks are you prominently using, as well as what storage systems you're using. So Amelia, looks like you've already started off a quick poll. Folks, it would be great if you could answer a question about your compute frameworks. What's the most common data processing framework you're using at the moment? And this time we'll actually be sharing the results so that you can see what everyone else is doing as well. Great. So that's interesting. A lot of Spark, some Presto, and continues to be a lot of Java out there as well, perhaps for running any kind of algorithms or models. And TensorFlow starts to come up, but not as much. So thanks so much for the feedback. Let's take a look at what storage systems you're using in the background. All right, we'll be closing this out just a second. So here are the results. It looks like there's a lot of HDFS usage. S3 is starting to get more popular. Continues to be a lot of network attached storage as well, and perhaps the other cloud storage and on-premise object stores are starting to come up as well. So this is exactly the reason why Alluxio, as well as why there's a need for a layer between compute and storage, because as the number of storage technologies evolve, and as the number of compute frameworks evolve, it becomes quite a complex task, an expensive task to connect every framework to every storage system underneath to truly get the value of data that you need. So let's move on and jump right into an overview of Alluxio. So, quick background on Alluxio for those of you who don't know us. Alluxio started off as Project Axion, actually, at the UC Berkeley AMP Lab, where a couple of other popular projects have emerged as well. Mesos as well as Spark came out of the AMP Lab as well. And Alluxio was established as a company that was driving the open source project. We renamed ourselves Alluxio in about 2015. We have good backing from Andreessen Horowitz, and we've had some good accomplishments along the way. But let's dive into the tech. So the tech, as we talked about earlier, you are seeing a lot of compute out there, different flavors, as well as many different storage systems underneath the covers. So Alluxio fundamentally is a distributed virtual file system that provides a unified layer on top of the storage systems underneath, where we provide HDFS drivers, Swift drivers, the S3 drivers that can be used for any object store that has an S3 compatible interface, as well as an NFS driver to make NAS storage a lot more accessible to big data and AI workloads on the top. And we call these kind of our now southbound side. On the northbound side, we have many different connectors for all the different data processing frameworks on the top. So Java, we saw that Java is still pretty popular. So our Java API is a native API. We provide the HDFS interface on top for applications that are already using the HDFS interface, an S3 interface, a Fuse interface, which is quite popular. Fuse is essentially provides a file system-like interface, a POSIX-like interface for frameworks like TensorFlow or Python-based frameworks that essentially just want to access a local file system. And then we have a REST API as well. And there's three kind of core capabilities and innovations that Alluxio brings that solves those three problems that we talked about earlier with the separation: data locality, data abstraction, and data accessibility. So the first one is a unified namespace. Let's jump right into it. So let's say you have a couple of different systems. You have an HDFS cluster or multiple HDFS clusters and some object stores as well. You can mount those underneath Alluxio, and from an application perspective, you essentially just change the namespace from HDFS, and the path and the file system path, all of that remains the same. And you just change the namespace, and now the same applications that worked on HDFS or S3 will start working and processing data from Alluxio. So here you see that you have folders, users, and that user folder gets pulled under Alluxio. You might have other buckets under S3, and that data gets pulled under Alluxio as well. And you get this notion of a single unified file system, which might actually live physically on many different storage systems underneath. Another way to look at it is actually through a simple Finder view. So let's say you have Alluxio as a folder, top-level folder. You could have multiple HDFS systems which can be mounted in. Can have an object store and NFS as well, and these get mounted in. Now note that initially when you mount an understore, it doesn't mean that you're actually copying all that data into Alluxio. Alluxio is a system where you are getting Alluxio moves that data from the understores as on an as needed basis. So we do a couple of metadata operations to get the first level to get two levels of depth of the metadata from these understores. And then the following data is pulled back in depending on the workload that is running on the top. We also support LDAP from a security perspective, LDAP Active Directory, as well as Kerberized environments. And so you can pass tokens into Alluxio just like you would through the rest of your system. And so the unified namespace essentially creates an abstraction layer where you can change underneath the covers, you can change your storage systems or move data around. But the second one, which we talked about, was data accessibility. And Alluxio's server-side API translation helps with making data across many storage systems more accessible. So for example, if you have data in S3, but your original workload, your Spark workload was written in HDFS, and you have moved over that data to S3, you can continue to use your Spark workload without changing any code using Alluxio. Spark will talk to Alluxio using the HDFS interface. Alluxio will then translate this into an S3 compatible interface, and it will know that this data now lives on S3 because that's what you have mounted in, and the application will continue to work seamlessly. So new applications can be built on old storage systems. Old applications can be leveraged to new storage systems without really changing the application itself. And it allows for seamless migration between one storage system to another through the different read and write paths that we'll talk about in just a bit. And then finally, intelligent multi-tiering. So by default, the data that is pulled into Alluxio is stored in memory. And so this is considered kind of hot data. This is your working set for your application, which might be a percentage of your total data set. So it could be 5% or 10% of your Hadoop data set, which means that only 5 or 10% of the metadata, as well as 5 to 10% of the actual data lives in Alluxio. But even for that data, you could tier it within Alluxio and store it either on RAM or SSDs or HDDs based on different policies. So LRU or LRFU or greedy algorithms can tier your data within Alluxio. And this helps bring data locality to your compute for the cost based on in a way that's flexible for your workloads as well as your cost requirements. So now let's take a look a little bit deeper. What does the Alluxio architecture look like? So here is the distributed architecture. You might feel like it looks similar to the Hadoop ecosystem, where we have a master as well as multiple standby masters. And then you actually have the workers themselves that are managing the data. So this data, it lives in the worker, and it could be in memory or in SSD or disk. And you're in a hybrid environment, in a cloud environment, as we talked about. If your compute is separated from your storage, you might have different understores underneath the covers, and Alluxio is co-located with the compute. So let's say you have two applications. You might have two workloads. Let's say a Presto workload and a Spark workload. Alluxio is either co-located within the same executor. So if you have a 100-node Spark cluster, you would have 100 workers of Alluxio that are co-located. Or depending on how much of your working set is overlapping across your compute, you could have a dedicated cluster of Alluxio that gives you a lot more data, that reduces data duplication so that multiple compute workloads can leverage a single cluster of Alluxio. From a metadata perspective, that is managed by the Alluxio master. And so the master is not only responsible for the file and object metadata, but also for the metadata within the Alluxio cluster. So which worker is managing which block of the files that you're working on. We have multiple protocols to select the master. So we have in the open source version, we have the zookeeper approach, and then in our enterprise edition, we use the raft protocol where you don't need a separate instance to manage to elect a master. So now let's move on and take a look at some of the the paths. How does data actually flow from your compute to your storage, and from your storage to your compute through Alluxio? So there are multiple scenarios, right? As you can imagine, depending on the workload, you could have you have read and write scenarios. Alluxio does support both. For a read path, your data may not be in Alluxio. It's the first time, or the data might live in the same node as the client, or it could live on a different node. And for the write scenarios, you could either write to Alluxio, only to Alluxio, but you have many different options. You could write to both Alluxio as well as the understore, where that data, which is a primary location for storage for that data. And you can do this synchronously as well as asynchronously. So for the purposes of, to make sure, we may not be able to go into all these scenarios today, but I want to show a couple of scenarios that you understand how the data flows through. And if needed, we can, please feel free, as a reminder, ask your questions. It's a good time to ask your questions so that once we get towards the end of the session, we'll try our best to answer as many as we can. So let's take a look at the read path. In the read path, we have the application, and the client essentially makes a request to the master, saying, I want to access a certain file or a certain file, and then the master knows where this file lives. In fact, where the block of this file lives, because a file could be divided across multiple workers if they're large files. And then if it is cached, essentially that worker will go and access it from its cache, either in RAM or in SSDs or disks, and send it back to the client, back to the application. And so you're fundamentally working at memory speed as opposed to going back over the WAN or going back over network speed and getting information back from the understore. Now, this is that scenario where the data may not be in Alluxio. And so the same flow sort of happens. It starts off the same way. The client asks the master. And in this case, Alluxio worker does not have that data and would go and ask the understore for that specific file and the blocks, and it would get pulled into Alluxio and then sent back to the application. You do have the option of caching at this point or not caching, depending on how that data is going to be used by the application. Now let's take a look at the write path. So in the write path, again, the client makes a request, and the Alluxio master tells the client which worker to write that data to. For most parts, it will tell the client to write the data to the local worker. However, there might be scenarios where the worker does not have space; it's out of space, and so there are multiple different ways that you can pick another worker that's close to this instance. We have rack awareness capabilities and so on that allow you to keep your data as close to your compute node as possible. Now let's take a look at a scenario where you want to write back to the understore. So in this case, not only is the data cached in Alluxio, but it is also going and being written into the understore synchronously, and then the application gets returned back. You also have an option to asynchronously write back to the understore. Hopefully that gives you a good idea of what the flow of data looks like between the compute and the understorage or the storage through Alluxio. Now, metadata access can also be very important, particularly for object storage. Metadata operations can be quite expensive. And so what Alluxio allows applications to do is cache that data in Alluxio. So it provides a local metadata lookup, essentially, for your compute frameworks. And so the application does not have to wait for expensive operations like listing a bucket or renaming a bucket. Alluxio speeds up these operations because they can be done asynchronously down to the understore or the object store that's underneath it. And so this can speed up workloads quite a bit as well. In addition, if you have um, uh, if you have data stored in Alluxio, the metadata is stored in the master, and the apps continue to assume similar semantics. So there's no semantic changes that are needed. So if you are using an object store API on the top, then it will assume that's the API that you're using and provide service that data out as using like let's say an S3 API. If you're using HDFS semantics in your compute frameworks, then Alluxio will serve it up using those semantics, and there are no kind of fundamental application changes needed to your compute. We also move out all the ACLs from HDFS, and so those get included in the metadata that's stored in Alluxio as well. Now let's take a look at some real-world use cases from this point. So hopefully you have an idea of what the overview, what Alluxio looks like as a system. But let's take a look at how it's being used in some environments, what the use cases are, and then we'll wrap up and open it up for questions. So here are some of the popular use cases that we've been seeing. The first one is sort of creating a mini virtual data lake across multiple HDFS clusters to co-locate the data with the compute and help with the separation, particularly in hybrid environments, as well as over time transition jobs or transition workloads to lower cost object stores. So that's one of the workloads and use cases that we've seen, and we'll take a look at one of the examples of that. Second one is machine learning productivity, and this is an interesting one. So typically for data science, the training data sets come from either HDFS or S3 storage. But what happens is that the data scientists don't have direct access or may not have direct access to these environments, especially if it's in a hybrid environment. And so there's data engineering that's needed or data pipelining that's needed to move this data physically from the data lake to the compute environment that the data scientist is working on. And this can take a lot of time. It's a manual approach and can affect productivity. And so what we've seen is that if you add Alluxio as a layer, you can service out data that the data scientists need, and it will look like their local file system, and they can continue to run their Python jobs or Python-based framework jobs that are using Python-based frameworks on that data without the need for this data engineering or data pipelining to move that data set physically into that cluster. Alluxio takes care of that data orchestration and brings the data locality to those environments. And we've seen in some cases the model training being done 2 to 4 times faster, and so you can get more models into production. And then finally, self-service data. So being able to make that data that you have across many different storage systems a lot more accessible. Because essentially, Alluxio provides many different ways of accessing the same data, but in a language that different people use. So whether it's Java, whether it's a local file system, whether it's HDFS or S3, you can access data using the choice, the choice of API that you want without changing your application, and so your data will get leveraged a lot more. So it's a lot easier to provide a self-service environment. So let's take a look at one of the examples. So China Unicom is running Alluxio as a dedicated cluster, and at the moment I believe there's more than 100 nodes in the cluster, and they're using it to abstract for data abstraction across multiple storage systems. You see here, it's including a relational databases, but also HDFS and HBase and others. And they have a separated environment. So they have Spark, that's predominantly their compute framework, but they have multiple storage systems, and they use Alluxio to combine that data into a single environment depending on the business needs and serve that up to the Spark workloads. It is a containerized environment, so in some cases it's DCO. It's a version of Kubernetes and DCOS that they're using for some workloads, and for other workloads, it might be a physical machine. So you have flexibility from a deployment perspective. You could either deploy it on bare metal, you could deploy it in a container or VM, whichever approach you prefer. And so in this case, they essentially integrated Alluxio across a variety of systems. Note that in the case of relational databases, Alluxio cannot directly read that data because every database has their own proprietary storage engine and storage format, and so essentially they just ETL that data, put it into Alluxio, and then have that data more accessible on top. And you see some of the query workload times with and without Alluxio in these environments. The second one is a compliance use case, and this is a very interesting use case where increasingly different regions across the globe have a lot more data privacy and data regulations. As an example, GDPR in the EMEA region. In India, increasingly there are regulations on financial transactions, and so this data cannot live outside of the region for longer periods of time. It has to disappear, if you will, within a certain amount of time, or it cannot physically be moved at all and persisted in another location. And so that was the use case with Barclays, where they were trying to have data that was stored in Teradata more accessible to Spark, but they had regulations that they had to stand by. And so with Alluxio, they didn't need to persist that data in another location. They could use Alluxio in an in-memory mode, move that data from Teradata into Alluxio and run Spark in it and get global access to their data while still meeting all the compliance regulations. And then the last use case I want to talk about is retail. And retail, we're seeing a lot of similar environments where it's a Spark plus HDFS stack, or Spark plus object store and HDFS stack. And in these environments, especially in a hybrid environment, Alluxio can bring data locality, and depending on the speed of your network between your locations, you could see anywhere from 2x to 10x improvement. And so not only does it give you a performance boost, but it also helps with operational efficiency. And with that, I just wanted to make sure we talk about our project. So Alluxio is an open source project. We're seeing a lot of great momentum in our community. We have a growing list of contributors and a lot of downloads. We're Apache 2.0 licensed. So if you haven't given it a try, reach out to us. We'll be happy to walk you through answer questions on our Slack channel or in many different ways. We also have a new sandbox environment where you can try out Alluxio in a clustered environment as well. And Amelia, it's a good time now to open up for questions.
Great. Thank you, Dipti. That was a lot of great information, and I can see that we already have a few questions. As a reminder, if you wish to ask a question, please select questions from the GoToWebinar control panel on the right side of your screen. Our first question is, does Alluxio have to be deployed co-located with compute?
Yeah, that's a good question, Amelia, and I think it depends. The answer is it depends on what the workload is, what the working set of those workloads is. So let's say you have a couple of different computational frameworks that are processing data, and they are running on completely different data sets. If that is the case, then to achieve data locality, you would have Alluxio running co-located with those compute frameworks and in the same instance where your executor is running. So wherever your Spark job is running, that's where your Alluxio worker would be as well. However, we have seen many cases where they are overlapping data sets. So the data is being accessed by different frameworks, but it's actually the same data. And in this situation, you would want to create a dedicated Alluxio cluster It would still need to be very close to the compute because that's one of the, at the end of the day, you want to maintain data locality. And so you could then have a dedicated Alluxio cluster, which multiple computational frameworks are using to process data.
Great. Another question we have is the open source version of Alluxio seems to support 3 understores, one of them being the in-memory option. Is that the limit, and would it be possible to have more? And what is the maximum number of understores that can be added to a single Alluxio cluster?
Right. So Alluxio can actually support any number of understores, and we are for the enterprise edition, there's really no limitations on the number of understores that are supported. You can use Alluxio just as an in-memory file system if that's what you like. So that's a good use case for transient data. So if your workloads, let's say your Spark job, is creating a lot of intermediate results that are then being used for another set of jobs, then you may not want to actually persist this data to an understore at all. You might just want to have it in data, in memory, this data in memory, and then once the compute is done, you can essentially take down that Alluxio cluster as well. So that is a good option. You can run Alluxio without any understore because it basically just functions as a local distributed file system, providing you all the capabilities you would expect, from a file system. Great. So I think, Amelia, let's see if there's any more questions. All right, folks, if you have any questions, now is a good time to ask those questions. We'll hang on for a couple of minutes, and then we'll wrap it up. So please go ahead and ask any questions you might have.
Great. I want to thank Dipti for today's wonderful presentation, and thank you to our audience for joining us today. As a reminder, we will email you a link with the recorded webinar, and if you have any questions, don't hesitate to reach out to us. This concludes today's webinar. Have a great day.
Thanks, everyone. Thanks for joining. Bye-bye.